Well, just like with our normal distributions, there are two things that we can do with the t-distribution. The first is to generate confidence intervals. The second is to generate significance tests. So we're going to talk first about confidence intervals for our new t-distribution. And as I've said before, if you've bought into the methodology and into the inference toolbox, there's only going to be some minor changes. Obviously now using standard error instead of standard deviation is going to be a little different from chapter 10 when we did means using sigma. Some slightly different checks, but we're going to go through those now. And again, make sure that you look at the problems that have been assigned on the task sheet, read through the examples in the book, be clear on the differences between them, because now is the time of year where things start to become a little muddied between tests, and you don't want to be thinking you're dealing with a proportion when you're dealing with a mean, or claiming things that don't exist in the distribution that you're dealing with. Right off the bat, though, number one, population and parameter of interest. These haven't changed. What we're back to, though, is we're back to mu. We're back to a population mean. And we always want to be talking about the parameter of interest as a parameter, so please do not refer to X bar in your statement number one of your confidence interval toolbox. You want to be talking about mu, the population mean, for a given scenario. So that really hasn't changed. Again, you're going to write statements for these. In the beginning of chapter 11, everything's going to be one population based, so you don't have to do the two population statement like you did in chapter 12. Guess what, though? 11.2 is going to get you there. So mu, population mean again. All right, in step 2, we define what our test is, and in this particular case, since we're doing an interval, it's a one sample t interval. And once again, item number 1, SRS, we know that that is crucial because if the data that we collect is poorly collected, it doesn't matter what we do with it. The second check is a new one. It relates back to one that we've already done before, but it's definitely different because there's a second word here. It's not normality, it's normal enough. So the irony of using a t-distribution is it's a non-normal distribution. However, highly skewed t-distributions are really poor indicators of what the population is actually looking like. So we still do a kind of quasi-normality check, and it's the normal enough check. It should probably be called not overly skewed check, but that's not what it's called. So we're going to be looking at normal enough, so we're going to be looking at a couple of things that we've already seen before. The first is obviously if this is given. And you may be saying right now, if you're given that it's normal, why aren't we just doing it like we did before? Remember, we are now using S and not sigma. So sigma is the Z-based statistic, T is the S-based. I think I said that backwards. S uses T, sigma uses Z. So we're still using the T interval, even if we know that the distribution is actually normal. Obviously, other ways in which we can look at normality, looking at a graph of the normal probability plot, if we have the data, would be a way. Looking at other graphical representations, such as a box plot. You know, we know what the symmetry of a box plot looks like. We know if maybe we were given like a stem plot, we could look at a stem plot, or even a histogram. Again, we want to make sure that things are not overly skewed. So although we might not be able to confirm that it's normal, is it normal enough? Is it single peaked with a single mode in the middle, and you don't have to verify that it matches any type of 68, 95, 99.7, just that it's normal enough to use the t-distribution. And finally, obviously one that could get you the normal enough is the CLT, that if you have a large enough sample size that the sampling distribution of that particular set of data, regardless of the population it comes from, will be approximately normal. That is normal enough for us as well. So kind of adding in this this new one of looking at some graphs. This is the time where they often provide a stem plot or a histogram, and then using the old given normal probability plot, CLT. So the CLT is back on the table. It's been gone for a while since proportions don't use the central limit theorem. And then the final one is one that is actually not referenced in the book. I think it's still a good check, so I'm going to override the book on this one. And for consistency's sake, we always do a population versus sample size check, and we're just going to continue to do it. So we're still going to do our n greater than or equal to 10n check. Again, the book doesn't reference it. I'm telling you right now, though, for any problem that requires an inference toolbox that I'm asking you to do, I'm going to ask you to do this check as well. It's always a good thing to make sure that you're not oversampling your population, regardless of the test that you're using. So this is definitely a place where our book falls a little short. All right, so here's our confidence interval. It looks horrible when I have to try to type it on this, so I guess I will write it out. It's x bar plus or minus t star times our standard error of x bar. And that looks like every other generic confidence interval we've ever... Oh, that looks like it says sex. That's weird. Sorry, that was just bizarre. X bar plus or minus t star times the standard error of x bar is going to be what we're going to use. Again, I think I told you that on the formula sheet it says something like sample plus or minus critical value times standard deviation of sample is usually the generic wording. It used to be x bar plus or minus z star times standard deviation. Now it's x bar plus or minus t star times standard error. So this is what we're going to be looking at. Of importance, this little guy right here, t star. So in the last video I talked about what t was in terms of a test statistic. We need to talk about the critical value of t star. Well, t star comes from a Tchart. And many of you later on will figure out that you also have a way of getting t star in your calculator, which is inverse t. Now, my apologies to those of you with really old graphing calculators. You may not have the inverse t operation on your calculator, and unfortunately we just can't get it to you because you can't update your operating system. So we are going to be right now focusing on using the Tchart, and the other thing that we have to talk about is something called degrees of freedom. So degrees of freedom, referenced as DOF, are the, generically speaking, the number of values in the distribution you must know before you can predict the statistic for that distribution. So if you had n equals 20, I would need to know 19 of those 20 values if I knew the average before I could tell you the last value. In other words, there's no way to predict if there are 20 values given and I know the average. If I didn't know 2 of them, I couldn't tell you what the 2 are. But if I knew 19 out of the 20 and the average, I could solve for that one missing variable. So we always look at t star at n minus 1 degrees of freedom. So we look at the sample size minus 1 in the t star chart to get our t star value. So the next thing we're going to look at is what a Tchart looks like. All right, here's a Tchart. It looks similar to our normal distribution tables from earlier in the year, but it's slightly different. So the first thing I want to point out is what the two headings are. So if you look at the top heading, this is the tail probability for p. So this is essentially telling you what your p-value would be if you generated a particular t-value. And down the left-hand side, you will see that these are your degrees of freedom. So starting with degrees of freedom 1 and then going all the way up to, I don't know if you see it down here, it's actually infinity. And we start at degrees of freedom 1. There's no way to have 0 degrees of freedom because if you only sampled one person at a time, you're essentially doing a census, which isn't an inference-based type of thing. So we always start with a sample size of 2, which means that 2 minus 1 would be 1 degree of freedom. And then the values inside the table, all these values, these are your t-star values. These are your test statistically generated values. And down at the bottom, you'll notice that there's, let's see if I can move this a little bit. Yeah, there we go. Down at the bottom, you will see your confidence levels. So when we were doing Z-star, we knew that there was a particular Z-star for every confidence level. There's a particular T-star for every confidence level as well. So let's say for a second that we were dealing with a 20-person sample and we wanted to do a 95% confidence interval. We needed the T-star value for a 20-person sample at 95. Well, here is 20 right here. But remember, we're doing this at n minus 1 degrees of freedom, so we are going to go to 19. And 95% is down here. So if I kind of follow my 95% line up and I follow my 19 line over, my T star value would be 2.093. Meaning I would go 2.093 standard errors above and below my X bar value to generate my interval. Simple enough. Now, where things get a little bit tricky is what happens if your sample size doesn't fall on the actual table. So let's say that you were doing a 40-person sample. So you're going to go look for your 40-person sample, which would be 39 degrees of freedom. Uh-oh, no 39 degrees of freedom listed on our table. There's a 40 and a 30. You might say to yourself, 39 degrees of freedom is closest to 40 degrees of freedom, so I'm going to use the 40 value. That would be a bad choice. You always pick the T-star value for a conservative sample size. So at 39 for degrees of freedom, you would have to use the 30 line for the degrees of freedom in this chart, not the 40 line, because you basically want to generate a bigger interval than you would have if you had used 39. It's kind of like the worst case scenario interval based off of your sample size. So I would go to the 30 degrees of freedom, and let's say we were doing a 99%. So I would go to 30 degrees of freedom at 99%. My T star would be 2.750. Funny enough, you'll see as you get to the higher numbers, if you look at the T star values, they don't change much. So even for that, for 30 degrees of freedom and for 40 degrees of freedom, T star goes from essentially, let's see here, 2.750 to 2.704. Not a very large difference at all. And as you get up and up between 50 and 60, 2.68 to 2.678 to 2.660, you're talking about 18 thousandths or 18 hundredths of a difference. And as you get really, really high from 100 to 1,000, there's barely any change in your T-star value. Ironically, at infinitely many degrees of freedom, this line is actually the values that you use for your Z-star, because as the sample size goes off to infinity, the T distribution actually approaches the normal distribution. So these values of Z-star that we used earlier in the year are actually the infinitely many degrees of freedom, or just ridiculously large degrees of freedom. All right, so that's how you're going to use your T-star. If you're doing a problem where you are asked to indicate between what two p-values something falls, so if you're doing a test statistic-based thing, you may find that you have a 9 degrees of freedom, and your T value falls somewhere between 1.100 and 1.383, so like 1.24 is maybe your T value. If you get a T of 1.24 at 9 degrees of freedom, you would know that your p-value falls somewhere between 0.15 and 0.10. So from a decision-making prospect, if you're doing an alpha level of 5, this would be a fail to reject for that particular t-value. And as with other test statistics that we've talked about before, the larger your t-values, the more significant your results are. So if you kind of look in this top right quadrant, look at how large these t-values are. That's where your significant results are. So we're always looking for larger t-values to show significance, smaller t-values show that you're not very different from the claimed center. All right, final slide here is just your conclusion slide. Again, this isn't going to change, so we are blank percent confident that based on samples of size, so we want to get our sample size in there, so samples of size n, blah, 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 proceed with caution, whatever we need to do. It basically doesn't look any different because you're not quoting a t-value anywhere. nor are you having to state anything about the degrees of freedom because it's tied to your confidence level back in step 3. So you will be kind of noting that in step 3, but you don't have to worry about it here in step 4. So it very much operates the same way as a confidence interval did before. Now we just need to have that T star value. As you look through the book, they'll eventually talk about inverse T. I'm going to talk about it when we get to the next video. So if you want to play around with it and kind of look at the inputs, you can look at the inputs, but it's pretty easy. All right, so that is the confidence interval for a single population for a mean.